ladies and gentlemen, wave interactions. So we have four types. We have reflection, and we did the law of air hockey. We have absorption. Think heat lamp and nasty burger or black shirt out in the sun. Absorption. I should have a T in there. Diffraction, and that is sound bending around a corner. So we can say things about people even when they're around corners and they will hear us. And then there is refraction, which is when a wave goes from one medium, such as air, to something else like glass or plastic. So these are the four that we need to talk about, and let's see how it looks on paper. So over here, when a wave comes in and bounces off, and again, these are wave crests that are perpendicular to our direction or ray, comes in, bounces off, that is reflection. So a wave comes in, bounces off, like on a mirror. When something goes in, the wave's coming in, and all of a sudden it just disappears. It doesn't disappear. The energy of the wave, a wave is energy, has been absorbed by this block. That's absorption. Remember, the wave energy doesn't disappear. Conservation of energy says it's just gone somewhere else. It's gone into the thermal energy of the block. This is a wave bending around a corner, so if someone's standing here, they will still hear the sound wave. That is diffraction. And if a wave goes through a piece of glass and bends, that is refraction. That's how they look. Okay, at the end of the last video, after my daughter after she stopped it with the diverging lens, she said like divergent. So I'm not familiar with the story, but you can imagine something that goes away from each other is divergent. All right, so now we're going to take a laser off of a mirror. So this is a mirror, as it says in the problem. The ray comes in, hits the mirror. Now, wherever it hits the mirror, we draw a perpendicular line. That is called the normal. The law of air hockey says that this ray bounces off, okay, just like that, and that these angles have to be the same. So this is the incident ray. It's coming in. This is the reflected ray. It has been reflected by the mirror. This is the theta incident. Remember, theta is just the Greek letter for T. And just like in math, we can use T, X, Y, whatever. So we're saying theta in and theta reflected. Not out. Jenna says out, which is another way to say reflected, but it's theta reflected here. So we have to say that these two angles are the same. So in math, we put a little line like that through them. So we have incident ray, reflected ray. We have the normal line, and we have the incident angle and the reflected angle. All right, ladies and gentlemen, almost done. So here comes our laser. This is the hardest one of all. Wherever it hits the surface, we draw a normal line. Now this is air out here, and let's say, like in the lab, this is glass. If this glass wasn't here, the ray would keep going in a straight line. But we know that refraction means light bends. So it won't go in a straight line. It's going to bend and go a different way. Okay, so it bends and goes that way. This was the normal. So we have that one. Okay, so that's good. This is theta in. Again, theta is just the Greek letter T. So theta in. We have the normal. We have the incident ray. This is the ray coming in. What? Then we could call it what, Shanna? That's theta in, but theta out, so to speak. So this is the refracted ray.
Oh, so we're doing that one.
That's what we're doing, Shanna. All right, so that's the refracted ray. The angles are always with respect to the normal. So this is theta refracted. So this is the hardest interaction we do. Light bends. This is why the pen looks like it breaks in glass when it's in a glass of water. Why the light bent as it went through the block in the lab. This is what's going on at this surface. Alright, last but not least, so we want to draw a diagram of wave crests as they pass through a slit. Before going through the slit, the wave crests are parallel. Okay, so here's the direction the wave is traveling. So remember a ray, if the wave is traveling this way, so this is the ray, the wave crests are perpendicular to that ray. So here comes the wave crests. As they come in, it's going through the slit. Now diffraction says that as rays go through a slit, they bend when they come out. So they bend around corners. So if someone were standing here, and this were a door, and you were standing here shouting, they would hear you. And the reason is, it's because the waves bend as they go through that slit, and that person can hear you talking through a door. So when we sent, I can't remember all the classes, but I think Karen in one class, Bikram in another class, and I don't remember who was in second period, but this is why they can hear us when we talk in a room and they're around the corner or outside of a door, and that is called diffraction. Okay, so this is diffraction of waves as they pass through a narrow slit. And that's it, that's the homework. I hope this helped. If you have any questions, definitely ask. My daughters wanted to say goodbye, so I wanted to thank my daughter Denali and Shenna. Go over here, she wanted to say goodbye, so say goodbye.